Okay. I wanted to get back to you about this this problem here. Remember this one where you had a disc of metal and you cut out a sector. And then we cut that out and we made a cup out of it, right? A cone. Okay, so this is what we came up with, our volume function, 1/3 pi r squared h. And so you remember that we had this h. This was the radius of the original piece was 20, and that ended up being this edge right here, right? So then our radius of our cone was r, and then this is h. So the volume of the resulting cone, 1/3 pi r squared h from the Pythagorean theorem, square root of 20 squared minus r squared. And then we got r using arc length and angle in this circle here. So we said it was the whole circumference minus that. So the whole circumference minus that, and then to get theta, we would divide by 2 pi. Okay, so the question was, this is going to be an awful derivative. What does it got? It's what's the structure of it? What's the big picture? Product rule, right? But then within the product rule, for the first one, we have a chain rule, not too bad. Second one, we have like a 3 deep chain rule. Okay, so we got the product rule, and then both of them are chain rule. One of them being like 3 deep, right? It'd be a square root function, and then it'd be a square function, and then it'd be negative 20 times, right? So we were thinking, so is this the easiest way to do it? So looking at this, so immediately I see that, well, we got r squared in both places. You see that? And they're identical. So r is just this direct function of theta. So we could just as easily solve this as a function of r. So rather than take the derivative with respect to theta, take the derivative with respect to r. And then just go back and find theta later once we get the right r, right? Does that make sense? So much more manageable. And we can do even better than that. Notice that both of them are r squared. So we can just, I called capital A, r squared. So now I've got my volume function as a function of r squared, which is perfectly valid, and that's what it is. So it's getting easier with every simplification here. So then I went even one step further. I put the a inside to take away the product rule. So now that's the same as 400a squared minus a cubed. So I took the a to the outside and made it a squared on the inside, right? So now I'm gonna now I'm ready, and all it is chain rule. So much easier first derivative. Okay, did I lose anybody?
Where did you get the a cubed?
All right, what is a? A is the same as the square root of a squared. So it's just about being confident with algebra. A is the same thing as the square root of a squared. So I'm just taking this a and putting it inside as a squared. Yeah.
Okay. I feel like a lot of the trouble I'm having is with the algebra and the setup of it. So on the test, is it going to be possible to still get points if we can like set it up right, even if we can't necessarily get that?
Yeah, I'm going to test you on all aspects of this. The setup, the understanding of the quantities, the setup of the function, using the calculus to optimize, everything you'll be tested on. So you don't, if you make a mistake, you're not going to lose points for all the rest. Does that answer the question? Yeah. Yeah, so I'm aware that there's so many facets to these. I want to see about what you know about each part. You get the chance to show me your understanding of all the aspects.
I see you get the a squared. What did you get a cubed? Oh.
Okay, so I got this volume now as a function of A. Yeah.
I never think
Yeah.
To see how that would back in the R squared.
So this was our volume function for theta. That's what we came up with in class. I never wrote that out, but that's what we came up with a couple days ago in class. So I noticed, well, this would be a lot easier to just make as a function of r, because there's just a direct link between r and theta, so let's just do it in terms of r. And then I said, oh, look, they're both r squared, so just make capital A equal to r squared. And so now we're down to this, right here, which is much, much easier, and we can make it even a little easier by taking that a on the outside and putting it on the inside as a squared. And so now ready for derivative. This should be v, so v prime here. Okay, so that's the derivative. Okay, and so we get a ratio, but we're interested in where the derivative is what? 0. So it doesn't really, we don't really care about this, because what makes a ratio, what makes a fraction 0? What makes a fraction 0? Top is 0, right? So I just thing meaning this. So all we really care about is this right here. 800a minus 3a squared. When that's 0, we've got our critical point. So I went through and solved, and I got capital A was 800 over 3. Okay, so capital A is 800 over 3. So then the radius, corresponding radius, would be the square root of that, because we said capital A was r squared. And then theta would be, just take that radius and plug it into that expression that we got for theta. So I came up with this angle, 1.153, as the angle that would maximize the cone. Okay, so what I did next was I graphed the original volume function. So here's the original volume function as a function of theta, right? That's our f function, this one. So x is theta. And so then I was checking my answer here. So I came and I looked at the max. And sure enough, the x value of the max right there, 1.153. So that's the angle in radians that you cut out to get the maximum volume. And then the maximum volume is 3224 centimeters cubed. Just confidence in algebra and recognition of what you have made this a much, much easier derivative than trying to do this with respect to theta. It'll work, but this will be an awful derivative, right? Like we said, product rule with chain rule in it. So get an easier version, and then once you get that value of A, which was 800 over 3, I back calculated the angle right here from the angle as a function of r. Okay, any questions? All right, so on your homework, was there one of those we want to talk about?
Maybe the last.
What was the last one? 1 divided by 1 plus x squared? And I was having you start at what, 1.5?
Yeah.
Okay, so here's just a general question that's really important. How is it that we've become able to find closed form exact accumulation functions from rate functions? How is it that we've been able to find closed form exact accumulation functions given the rate function? Talk to the person next to you. Go. Okay, so here is okay. So what was the response to that? So we've got this closed form rate function. How is it that we've what is it that we've developed that allows us to find closed form accumulation function from rate? Anybody? How is it that we know how to do that?
Well, at the beginning, we
Sorry,
started with the step.
can you raise your hand before you start talking? Yeah.
Okay, so basically you just do f of x minus f of a of the original function.
Okay, but that's still not the actual closed form, like in terms of formulas that we know, right? So yeah, f of x minus a. What is that, for instance, for this one, and how do we know what it is? Does my question make sense? So what function is f of x minus f of a, and how is it that we're able to know it?
It's the accumulation.
Okay. But I'm saying, like, is it sine x plus x squared over 2? Is it e to the x plus ln of x? How do we know what it is? How can we get these, given a rate function, how can we get its closed form accumulation? Sure. Okay. Antiderivative, so what's that?
The original function that this is the derivative of.
Right. And how do we know what that is? How is it that we know what that is? What's that? Did we memorize rules for finding closed form accumulation functions? No. What rules did we learn? For finding rate, right? So we learned all these rules for finding rate functions from accumulation functions. So when we learned those rules, we didn't learn just one thing. We didn't learn rate of change. We learned something else too. What did we learn? Accumulation functions from rate. We just got to think backwards. You see? So what is the accumulation function? Okay, arctangent. So you learned the rule for the derivative of. You learned this rule that said that the derivative of the arctangent of x dx was what? So at the time, you thought you were just learning one thing. You thought you were learning, oh, this is the rate of change function for this given function, right? This is the rate of change function for the arctangent. But you were learning two things. What was the other thing you were learning?
The accumulation function for that.
Right. So tangent inverse x is an antiderivative or an accumulation function for this rate function. That's how we're able to find closed form accumulation functions, is from all the stuff we learned on the mastery by thinking backwards and applying the rule in reverse. You see? Okay, so how are we going to check? So how can we check this? This is our open form of accumulation, right? So how do we check it? So at first I was giving you these, right? But now I'm not. So what is it? Arctan of x. All right, so now we want to graph so Daniel, what will the closed form of this be? Now that we know that fx is arctangent of x.
So it would be arctangent of x.
Uh-huh.
Arctangent of 1.5.
Right. Are they the same? They're the same. So, because we trust this one, right? We trust this one. We know that exactly what the integral function does. The integral gives us accumulation from 1.5 to x, accumulating at this rate. So then we do some algebra and we get a closed form. Trusted? Which one do we trust more? First or second? First we trust. We know what the integral does. Why don't we trust this as much? What's that? Yeah. Could have done our math wrong, could have done the algebra wrong. So that's why we check it against the open form. Okay, other questions? So is there more to discuss about this particular example? Anything else? Does it make sense? So we started out building accumulation from rate. We're only able to build the open form. Okay? Then we did rate from accumulation, and we found that with the average rate of change, the open form, we could create closed form rules for rate from accumulation. And now it's knowing that we go back to finding accumulation from rate, and we can get closed form accumulation from rate. Does that make sense? So what I just said was really important. It's kind of, it summarizes our journey and why we did it in the order that we did. See, back in the beginning, we couldn't get closed form accumulation from rate. We couldn't get that until we learned these rules for closed form rate from accumulation. And now given a rate function, using those rules in reverse, we can come up with closed form accumulation from rate. That's what we're doing. Okay. Any questions, comments? All right, so where are we at here? So this was the slide we were at last time. Given a rate function, how many accumulation functions does it have? Right? Each one of those is an antiderivative. These are all antiderivatives for that rate function. Okay, and we said this one was f of x minus f of 1, or x to the fourth minus 1 to the fourth. How do we know, how can we check to see that this is an antiderivative of this? Take the derivative. And we get 4x cubed. Okay? So we did all these. Each one of these is an antiderivative. And because we know what original function has this as its closed form rate, then we can find each specific accumulation function. And we said the improper integral represents all antiderivatives, or the whole family of accumulation functions for that rate. Okay? That's what the improper integral. Improper meaning no, you won't see any limits there. It represents every single one. Every single one of the antiderivatives of 4x cubed, or the whole family of accumulation functions. Okay, so we know that it comes from subtracting a to the fourth, but that's really just plugging a to the fourth into f, right? So that's just a constant. So this is another way that we write improper integrals as x to the fourth plus c. So what does c equal? So here's the general form then. F of x minus f of a equals f of x plus c. So what does c equal? What constant is it specifically? A? C equals A. What does it equal? Negative f of A. 0. What does C equal? F of A. So I've got A, 0, f of A, and negative f of A. Negative f of A. All right. Okay, so again, representing the whole family of closed form accumulation functions, or all the antiderivatives for that rate. Okay, any questions on that? So, in order to, just like we had to be masters of finding closed form rate from accumulation, so now the reverse is kind of like the next level in difficulty of thinking and working it out, right? So in the first, to find closed form rate from accumulation, we just applied the rules. Well, now we have to know those rules so well that we can apply them in reverse. So we have to have a little practice of that. So this is an easy one, right? You just look at this and you go, oh, okay, so what function, and we say this for all of them, but this one's more easy. So we ask, what function has this as its derivative? What function has this as its derivative? And of course that is x to the fourth. So that's the question we ask. As these get tougher, we still ask that question. Keep that in mind. We're asking what function has that as its derivative? All right, we can skip this. So let's practice. So to be really good at derivatives, or to be really good at finding antiderivatives or reversing these rules we've learned, we have to really know the rules well. So let's review. So I've just rapid fire, just like the mastery test. So find the derivative of each of these, or the rate of change for each of these functions. Find the rate of change function for each of these functions. And I had handouts for you, but I forgot them, so you just have to write them. You just have to write them down. Just so fast. We don't take a lot of time on this, but we do want to review and get the rules in the forefront of our mind. Derivative. In order to be good at antiderivative, we got to make sure we've got derivatives down pat. So these are derivatives. You should have been on the fourth or fifth one by now. Write them down. Get some notes. Write them down. Okay. Adelaide, 9 to the x.
So, 9x
Okay. Megan, negative 20x. Richard, x squared over 5. Let's see. David, x squared over 5. 2/5 x. Cosine radical x. Stanley.
It's negative sine of square root of x times 1 over 2 times square, or 2 times square root of x.
2e to the 6x. Corey,
I did not get this one.
do it. On the fly. You can do it.
I don't remember how to do all these. The x is in the exponent.
It's the same.
E to the x. What was the derivative of e to the x?
Oh, it's e to the x.
Okay, but now you got e to the 6x.
So it's e to the 6x times 6 of 12 e to the 6x.
Good job. Marcus, negative 6 ln of x.
It was 1 over 6.
1 over x?
1 over log.
No, just 1 over x. And what is negative? What happens to the negative 6?
Negative 6 over 1 over x.
Negative 6 over x. All right, this one. So we don't want to do quotient rule. So how do we want to start on this one?
X is the negative.
Judith.
You can make it x to the negative 3/4.
Okay, and then?
So then you put the exponent out front. So it's x, times x, and then negative 7 over 4.
Okay, negative x to the negative e. Tyler.
Negative x to the negative e, you can bring the negative e down into the product.
Okay.
It's going to be e times by x, the negative e minus 1.
10 over x to the 21st. Sharon.
Negative 200
X to the e to the sine x. Christina.
Cosine x times e to the sine x.
Any questions on these? So you see when chain rule comes into it, it's going to be a little trickier. So we got to practice this, right? You got to recognize, you have to see a function like this and recognize it as the result of one of these rules that we've learned. And with chain rule, it's like, oh, now there's two things I got to look at, but it ends up collapsing back into one, right? So let me do this. Why? Okay, so now, antiderivatives. I'm going to put our work that we just did over to the side, okay? So now you're going to try to find antiderivatives, and I'm going to... Too big. Hopefully you'll be able to see it. All right, so there's our work that we just did. I'm showing you, I'm going to show a few more. There we go. Okay, so now, antiderivatives. Here's the work we just did finding derivatives. See how many of these antiderivatives you can find. Go. So yeah, yeah, that's good. Good point. We'll talk about that later. Yeah. What's an 8? Yeah, that's an 8.
It's beyond something.
Okay, so this requires some thinking, some processing, so you can talk with each other.
Mm-hmm. Oh, so it's taking the cosine the negative from this part.
Oh, it's just cosine. So it's cosine to the fifth.
Right.
Cosine to the fifth, okay, get that one, but what?
Cosine to the fifth, plus.
Because you always
Because
have that
because
constant.
you have plus
Why
1
didn't
here
you
and
give
then
us the
disappear.
integral, so we don't know
It just
how to get there,
disappeared.
like, you should get in the habit, right?
Yeah.
Yes. You don't have to, but I know it's.
We can do that one easily, just bring the power up and divide by it. So that's 2x's. So.
Yeah.
You guys read that back there? There's plenty of chairs up here, so come on up.
The third one's turn off the power. Bring the power up. And divide by 7. Yeah. Every time.
So when you do the 1 over 2,
What are you looking at? Cube number 4. Remember, it's a little bit simpler than the first one.
right, but
Are you way ahead?
This one is that side.
because it's ready.
This is.
When you have a square root, you take the derivative of it's 1 over 2, and then you gotta do the that's right?
Okay, as part of your homework for Monday, you're gonna turn in these. So might as well start now, okay? You're gonna turn in these for your homework Monday.
Yeah, let's write it.
What's that? Yeah, write them down.
We want that crazy secant one.
That's the one I'm writing now.
Yeah.
Does that say e to the 6x?
Yeah.
X to the 4. So that's gonna be 1 over 2. We'll get there, never mind. X to the negative 3. That's just 3x.
Negative 6 is.
Yeah. So what happened to you? What to do? So this more thirds. Because I didn't really get that.
No, because then we're just negative. It would be a negative, right?
But this is just reversed right now, right?
1 over.
The 4/3 x
1. The power that 1 is actually on the x is now moved. So it's There's x squared, and that squared became the coefficient.
Yeah, but then there's not, it's not x to the third. Squared, that's the only way it would be to a first power.
Okay, that works.
Okay, so.
Okay, my approach was good.
So this one's chain rule. So secant squared of x is tangent x.
Okay, so let's do just maybe 3 of these. Let's do 3, okay? So let's do, we'll start easy here. How about 14x to the 6th? So if this is the rate of change, then in general, what will the original function look like? In general? It'll be, right, so if with the derivative, the power goes what? No, derivative down, so antiderivative up. So we're going to have x to the 7th. Okay? So now, what is the derivative of x to the 7th? 7x to the 6th. And what do we want to have for its derivative? 14. So we got to make an adjustment. Okay, so how about this one? E to the 6x. So in general, what kind of function will give us a derivative in general of e to the 6x? E to the 6x. So then we have to, if we took the derivative of that, what would we get? 6 e to the 6x. We don't have a 6. So 1/6. All right, here's the key. You don't have to stare at it and say, I have no idea, so I can't write anything down. Why? You can just go for it. You can just go for it, and then what? Well, how do you know you're wrong?
Do the derivative.
Take the derivative of it. So you can just experiment. You can just go for it and not be afraid that it's wrong because you're going to take the derivative of it and compare it to what you started with. Okay? And then if it's not the same, then you have some information to make an adjustment. So don't be afraid to write something down that's incorrect because you can take the derivative and compare and make the adjustment that you need. All right, so how about
Yeah, that's secant squared magnitude.
okay, so here's what you got to see in this one. Look, right there. What is that? Do you recognize that? Right. So we could rewrite this as secant squared times what? 1 over. Oh, and then we say, oh, that's familiar, right? What is that about right there? One over 2 square root of x. We know what that is. What is that? Derivative of square root of x. So the overall structure of this is coming from what rule? What derivative rule?
Oh, square root of x.
No. That thing is coming from what? We got the secant squared square root of x times 1 over 2 square root of
Oh,
x.
it's the tangent of the square root of x.
So what rule is that? If it's a derivative, what rule is that? Chain rule, right? Because this right here is the derivative of square root of x. So can you recognize that as chain rule? Can you recognize that as chain rule and collapse it back together? What would it be? So give it a shot. Tangent.
Of the square root.
Give it a shot. And how can you see if you're right? Take the derivative. So what would the derivative of this be? Secant squared of square root of x times derivative of the square root of x. There it is.
finish that one? Can you do the negative x to the negative e one?
One more. You want to do which one?
The negative x to the negative e.
Perfect. What's the general rule? So what rule would be, if this was a derivative, what rule was applied? What's that? What's that? Power rule, right? So now if we're doing antiderivative, how do we handle power rule?
Bring the power up by 1.
We're going to do what to the power?
Bring it up by 1.
Add 1. All right, so now, how can we check? Take the derivative. What's the derivative of this?
X
Negative e plus 1 times
to the
x to the negative e. So now the question is, what adjustment do we have to make to this first attempt so that it'll look like this? Divided by,
negative e plus 1. Or just positive e plus 1. We need them, I guess.
well, the whole thing's got to be negative though. Yeah, so we don't want this, but we do want a negative.
So just e plus 1.
So negative 1 over negative e plus 1. Did you see what happened?
Isn't that positive?
No.
So when we took the derivative, we ended up with this coefficient that we don't want, so we'll divide by that first, but then we also get this negative, so we'll include a negative.
Can you just not have the negatives? Like both of the negatives? On
Okay, so if you're gonna take the negative 1 away, then what's your denominator gonna be?
E.
He's saying take out the negative out of the e as well.
Yeah.
Give it
Just
both
make it
negatives.
1 over e plus 1.
Nope, it's not 1 over e plus 1. You can do it, but you gotta do it right.
It's not the bottom term.
If you change this to positive 1, what are you gonna change that to?
With that negative 1.
What will it be?
Negative on the inside. It's only
What will the whole thing be? If you change that to positive 1.
1 over e minus 1.
So it would be
Wait,
x
so it's
to
just
negative
negative
whatever you want to
No. You're taking the opposite of the numerator, so you have to take the opposite of the denominator to keep it the same.
Alright, so make e minus 1.
What?
E minus 1.
E minus 1. So you could change it to 1 over e minus 1. But this is fine. Okay, so this is the general idea. So you're going to have, you should finish these. Finish these for Monday, and then there'll also be some my math lab. Okay, well, we got another thing to do here. Last chance. What's that?
You're going to put that online.
No, I told you to write them down.
But you will
So you got to get them from someone else. Yeah, so go to the video. Okay. So, we're ready to talk about the fundamental theorem of calculus. Does that sound important? Yeah. It's what we've been working for all semester. Okay, so we've been on a journey. So everything we've done, almost everything we've done, is about building up to this and understanding this. Okay, I think you'll find it not too bad. Okay, so here's the fundamental theorem. Let f be any, capital F be any antiderivative of little f of x. So, tell me what does that expression mean? So what are the meanings of these things here in this expression? So just tell me one detail about that. How about Andrew Laux? Just any one detail about this. Anything you want. There are many correct answers. Any one detail about the meaning of this statement. Oh, he went for the whole thing. Okay, so say it again. Great.
That's the
accumulation from A to X
Given the rate function.
with that rate profile, F, the left. Yeah, he said it all, okay? And if capital F is an antiderivative of little f, then what does this equal?
Oh, sorry, big F.
Minus capital F.
DJ.
It's gonna be capital F of X
Uh-huh.
minus capital F of A.
Yeah, that's the fundamental theorem of calculus. So you already knew it. You already knew it, okay? So that's what it is. Everything we've been talking about all semester, and especially in this last couple classes, has been about the fundamental theorem. So then if we plug, say, b into x, if we integrate, say, from a to b, then what would from a to b equal? Lauren? So now we're going to plug in a value for x, call it b. We're going to integrate from a to b. What will that equal? So now, using that function, if you actually accumulate to a specific specified value, then it's just f of b minus f of a. Remember the graphs, right? Rate function over here, accumulation function over here. What is this finding? It's finding the net accumulation from A to B. Either the process of adding things up bit by bit, or using the accumulation function, the final accumulation minus the initial accumulation. Remember all that? Okay, so this is worth noting. This property has enabled generations of people to do calculus without understanding calculus. Okay? Because what this has often become is just a formula to plug numbers into and crank out answers. Okay? But you guys know way more than that, right? You understand. We've taken the time to really understand what this thing is. Okay, any questions? Congratulations, you're smart. All right, you got a quiz today in recitation, and then homework for Monday. One more week. Oh, we have our next exam is next Thursday. Okay, so I think I've already posted your review sheet, and I'll send out an email with details. But Thursday is our exam. Yeah, I just haven't done it yet. Yep.
So you have to make this up. So you add one. Add one. Yeah, so it should be -1.
Hello.